Hello everybody. Today we're going to be taking a look at a data structure known as a linked list. So far this semester we've covered I guess two other data structures. We've looked at stacks and we've also looked at queues. And actually in each of those examples we were relying upon a linked list to support the data structure. So the stack that we looked at relies upon a linked list. The queue that we looked at relies upon a linked list. And linked lists actually exist independently of both stacks and queues. However, it's important to keep in mind that a linked list can be used to implement either a stack or a queue. So what are the characteristics of a linked list? We have a head, and the head of a linked list is the memory address or reference of the node that is first amongst all the nodes which comprise the linked list. One may also designate a tail in a similar manner, holding a reference to the node at the end of the linked list. And the programming language Java supports what are referred to as references, and a reference is essentially a memory address. However, Java is to be distinguished from other high-level computer languages that descend from C, because Java does not support pointers, and in some other high-level computer languages, such as C++ and C, and I think in some of the Microsoft dialects like C Sharp, you may find varying levels of support for pointers, and it's just an important thing to emphasize that Java does not support pointers, and that Java supports something known as a reference, which is an address, much in the same way a pointer is an address. However, in Java, there's a lot less flexibility for how one can work with references as opposed to similar operations in C or C++, in which you can do something known as pointer arithmetic, which in certain contexts can turn into security concern, and that's something to keep in mind. However, Java doesn't support pointers, and since Java doesn't support pointers, it means that Java doesn't suffer necessarily from the same security weaknesses that other C descendant languages suffer from. Some additional characteristics of linked lists. The nodes utilized by a linked list support references going in both directions. And if this is the case, the linked list is said to be a doubly linked list. And in doubly linked lists, if the head node contains a reference to the tail node, and the tail node contains a reference to the head node, the doubly linked list is said to be a circular doubly linked list. And that's probably about as complicated as linked lists can get. And if each node in a linked list contains a key having a sortable value, the linked list is said to be sorted if the nodes are maintained in the order in which the keys are in order, starting at the head and proceeding to the tail. So we have doubly linked lists in which our node supports a previous and a next reference. We have circularly linked lists in which the first node has a link to the last node, and the last node has a link to the first node. That's what makes a linked list circular. And then we also have the possibility that if we're maintaining the keys in each of the nodes in a particular order, that and it makes sense to do so, then we can also sort the linked list to make sure that the key in each of the nodes occurs in a certain order that's prescribed by the type of the key. So if we're talking about an integer, for example, and we're referring to natural numbers, which are the positive integers, then that basically kind of precludes um, the way we can order nodes containing keys of those sorts of types. So we have the first method we look at that's implemented for a linked list is a search method. And here you can see we have a couple parameters, L, which is our linked list, and K, which is the key that we're looking for. And if you look at the pseudocode here, you can see we're just using brute force to determine if a given key occurs in the linked list. And that's just a while loop with this compound logical expression. And when the while loop exits, X, which is a node, is either going to be null or it's going to contain the address of the node containing the key that we sought to find. And here's an insert method. You can see we're talking about two parameters again, L, which is our linked list, and X, which is the key we're inserting. And actually, in this context, X doesn't just simply represent the key we're inserting, it represents a node containing the key that we're inserting. And that's something we'll look at in a little bit when we examine the implementation of the node. This method, list insert, is provided with a linked list and also a node containing the key that we'd like to insert. And we're just setting x.next equal to list head. And if the head of the list is equal to null, we're setting lhead previous equal to x. And then lastly, we're setting lhead equal to x. So you can see what we're effectively doing in this method is we're splicing in a new node at the front of the linked list. And then we also have to remember to set the previous reference of the node that we insert equal to null. Because of course, in this example, we're not implementing circularly linked lists or circular doubly linked lists. If we were, we would then set x previous equal to tail or end, whichever name we can pick for the end of the linked list. We also have a method to delete a given key, and the key is provided in a node object. L is our linked list. X is the node in the linked list that we'd like to remove. And you can see, or checking to see if the previous node is not equal to null. If that evaluates to true, then we know we have to update the previous node next reference to x next. That essentially routes around x, which is the node that we're deleting. Otherwise, we're talking about the head, in which case we can just set lhead equal to x.next. And then finally, we want to check to see if x.next is not equal to null. Because if that's the case, then we have to point that node back at x, which we do here, x.next.prev equal to x.prev. and we've essentially routed around X. And once X is dereferenced in Java, that memory is allocated for or marked for garbage collection, in which case that memory can be reclaimed and used for other purposes. We also have an augmented delete method, and this is a simpler than the delete method that we just looked at a couple slides ago. Again, we're talking about two parameters. We have our linked list. We also have a reference to the node that we'd like to delete. And you can see in just two statements, we can effectively route around X. And by doing this, that memory that's allocated for this node X gets marked for garbage collection. And when garbage collection occurs, that memory can be reclaimed for other purposes. And here's an augmented search method. You can see list search in this slide has two parameters, linked list L and key K. And we're also introducing an additional concept here, which is a nil node, which we can use to separate the node at the front of the linked list from the node at the rear of the linked list, making the assumption that we're implementing a circular doubly linked list. So here we set X equal to head, which is simply L.nil.next. And then we're using a while loop to iterate until we either encounter the key that we're looking for or we get to the end of the linked list. And when this while loop exits, this variable X, which is a node, will either be equal to null or it will be equal to the address of the node containing the key that we were looking for. And here's an augmented insert method. And again, we're making the assumption that insertions occur at the front of the linked list. We're setting x.next equal to l.nil.next. And then we're setting l.nil.next.prev equal to x. And then finally, we're doing a couple additional updates to the references in these nodes. We're setting l.nil.next equal to x. And then finally, we're setting x.prev equal to l.nil. So l.nil is always going to be right at the front. L.nil takes the place of front. And we were, in a couple of the examples we were just looking at, we weren't utilizing this sentinel value l.nil. But l.nil is used to separate the front of the linked list from the back of the linked list in the implementation of a circular doubly linked list. And so here you can see this is an illustration reproduced from the text. We have our linked list in its initial state, which is up here in part A. And then it looks like we insert 25, and 25 gets stuck in right at the front of the linked list. And then it looks like we remove 4, in which case we route around 4, and this node containing the key of 16 ends up linked to the node of the address of the node containing the key of 1. And one other thing you might notice is the use of these diagonal lines. The diagonal lines are used to represent null in what is essentially a reference. So when we build the node class, we create attributes for a previous link and also for a next link. You can see that's depicted here and here. And then those references, when they don't assume the value of an address of another node, are said to assume the value of null, which is represented by this diagonal line. And here you can see a circular doubly linked list with a sentinel. Our sentinel is this node that's depicted here in dark gray. And we're essentially looking at the same example that we just looked at, except in this example, we've augmented the linked list from a doubly linked list to a circular doubly linked list with Sentinel. And you can see we have our linked list. We insert 25, which gets spliced in at the front. And then it looks like we remove 1 instead of 4 in this example. And 1 is at the tail. And so in our implementation of a linked list, we have a node class, and that's depicted here. You can see we have public attributes, and we also have a public constructor. We have an isEmpty method, which just simply evaluates front is equal to null. If that's the case, then the linked list is said to be empty, in which event this method is empty would return true. We also have our insert key method. And if you have already looked at the pseudocode that we previously examined, the way this method is implemented is in accordance with the insert method that we just looked at in pseudocode form. So you might want to go back to that slide and take a look at the pseudocode to see the correspondence between the pseudocode and this implementation here in Java. We also have a find method, and again, we're just using brute force to find a given key. You can see we have this compound logical expression, and as soon as that evaluates to false, temp is going to contain the address of the node containing the key that we were looking for, or it will be null. Those are the only two possible outcomes. We also have a remove key method, and this actually is quite sophisticated, but again, don't worry too much about it, because if you go back to the pseudocode for the delete method that we just looked at moments ago, you'll find that there's a pretty close correspondence between this implementation in Java and the pseudocode that's provided that can really be used to inform an implementation in the language of your choosing. So it's not just Java. You could do it in Python. You could do it in C. You could do it in C++. And here is our display method, which enables us to see the state of the linked list. And this is very simple, just a while loop stepping over the linked list and printing each key. And then one thing I also like to do is to put this special formatting in, which makes the keys kind of pop out. And then I also put a tail in at the end to indicate that the linked list has been displayed in its entirety. We also have our app class, and you can see we're doing some insertions, we're doing some removals, and we're displaying in between. And if you look at the output, you'll be able to confirm that the implementation that we've looked at functions the way that linked list should.